a series of our ASA ECR seminars or symposiums. Our first speaker is Dr. Guilia Santucci, sorry, and she's from UWA, and you can see works with the International Centre for Radio Astronomy, and you've just finished your post, or just about to finish.
Yes.
4 weeks from finishing your postdoc. Exciting.
Yeah, it was scary.
Yeah, it was scary. It was scary. And the title of the talk was meant. Well, no, it's still the same. The number is different though. Basically, she studies galaxies, galaxy mergers, and evolution. And I'll let you take it from here.
And she did her PhD here.
Oh yeah.
I was gonna say that
Sorry. She is an alumna of this university.
Much improved from this morning. Yeah.
Yeah. Not alumnus.
Well, thank you.
Seems like I'm not the only person who doesn't know it. Go for it.
Thank you.
Sorry.
I think it's
your man.
alumna. Yes.
Yeah.
Yeah, it's a gender thing.
So yes, so I did my PhD here with Sabi. I had a great time, and that helped me to go into all of these things that I'm going to talk today. I've been working on these connecting stellar orbital structures with galaxy evolution for the past 1.5, 2 years. But specifically for this project, but I've started when I was doing my PhD here, and so that gave me the basic things to work with to go on and do this by myself. So before starting, I'm just going to give you some introduction of the things that we're going to need for this talk. But if I forget anything, if I say something that you don't understand or you have no idea what I'm talking about, please just ask me. You can interrupt me anytime. I'm happy to take questions anytime. I'd rather have you interrupting me and understanding what I'm saying instead of just keep going without having any idea what I'm doing at all. So let's start with galaxies. So probably the first thing that comes to mind when you think about galaxies is the Milky Way or something similar to that. So a spiral galaxy with bright stars, lots of gas, lots of things going on in there. Of course, we still have stars being formed, and so this is called a star-forming galaxy. But we also can have something that looks more like this. This is more round in shape. Oopsie. Yellowish in color because all these stars, the young bright stars that we've seen in the other galaxy, have died a long time ago, and so only the less massive yellowish stars are left. And this is because the galaxy has stopped forming stars a long time ago, and so these are called passive galaxies. And as you can already see by just the visual morphology, they have very different structures and things going on. But even if we look at galaxies that look the same, we look at other properties inside them, for example, the rotation of the galaxies or the stellar population of the stars inside them, we can still find differences. So of course, what we astronomers want to know is how do they come to be what they are today? Can we look at them today and at their properties and understand what made them become what they are? And of course, this is really hard to do with observations. We have simulations that can help us with that since we can look back in time. And our current understanding of galaxy formation suggests that these massive galaxies form in a two-phase process. During the first phase, we have that the galaxy forms stars in situ in the inner region. This is up to redshift about 2. And after that, we have the accretion phase where stars from external galaxies are being accreted to our galaxies that we are considering. These are called ex situ stars, and they can come from galaxy interactions, mergers, and so on. And so the evidence of these accretion scenario are predicted to be preserved into the kinematics of galaxies. And so that's what we can look at in our observations to figure out what happened to these galaxies in the past. But of course, we also have, as I mentioned before, simulations where we can actually see. Of course, we don't know if this is completely correct or not, but we can see what's going on. So I'm just going to play the video and put the audio because I like the music. I don't know if you can see it.
This is the music listens to the same.
But I'm curious which person in TNG put that together, because I know some of them and they don't associate with them.
All right, I'll just. Okay. So as you can see, there are lots of things going on. Stars moving from one galaxy to the other. The shape of the galaxy and colors changing with time. And so, what we want to understand, and what I was trying to understand, was if we look at the stars and the orbits of stars in these galaxies, can we learn anything? Because from simulations we know that, and from predictions, the stars on different type of orbits are predicted to come from different ways, to have formed or have been accreted in different ways. And so I was looking at the orbital distribution, so the orbits of the stars in the galaxies. But before going into that, I just want to give you a brief introduction on what exactly I mean with orbits of stars in galaxies. Sorry, there was the slide that I was supposed to have now. Yes. So I was looking at the orbits of galaxies. We have different type of orbits. So one of the orbits that we were looking at are the cold orbits. These are, as you can see there, you have the Y and Z axis, so orbits that are on the plane of the galactic plane. So they don't really have much velocity dispersion with respect to the Z axis, but they are in the galactic plane, as you can see there. And these, you can think of this like for us in particular as a thin disk. So stars that are rotating in a thin disk. And remember cold orbits because we're going to use that a lot, but I will keep saying this many times. But then we also have orbits that are more chaotic. They go all around. This time this is the Z axis, so they go all around the galactic plane, but also outside of it. They can be different types, but in general we call them hot orbits because they are not rotationally supported as the cold orbits, but they are pressure supported. So they have a high value of velocity dispersion with respect to the Z axis. And then we can have, you can think of these as stars in a halo or a bulge or something similar to that. And then of course we can have everything in between that we call warm orbits. And these, you can think of these as a thick disk in a galaxy, for example, where you still have some rotational support, but also pressure support as well. And then of course, if you have most of the galaxy rotating one direction, you can still have some stars rotating in the other direction. And we call those counter-rotating, obviously, orbits. Okay, so what did we do with these orbits? We took galaxies from the Eagle simulation, this hydrodynamical simulation, cosmological simulation. We took the 100 megaparsec box and we analyzed the galaxies, 3,500 galaxies there, looking at the orbits and how they change with time, with different masses and so on. In particular, how do we characterize these type of orbits though, if we look at a galaxy? So we took the angular momentum of a circular orbit, and then we measured the angular momentum of all of the orbits in the stars in the galaxy, and measure a ratio between that, their angular momentum and the one of the circular orbit. So this is called lambda z in our plot. We did then this lambda z value versus the radius. So if you have a value close to 1, it means that the orbit is very circular, close to a circular orbit, and we call them, as I said before, cold orbits. They're going to be in blue for the whole of the presentation. They're easy to remember. And then if you have something that is a little bit less supported, so not exactly as a circular orbit, we call it warm orbits. And then we have the hot orbits close to 0, so they're completely different from the circular orbits. Actually, not much, because they can be circular orbits in a different plane as well. But if they're not in the galactic plane, they're called hot orbits. And then we have the counter-rotating component that is similar to the warm and the cold, but rotating in the other direction compared to the two main ones. Okay, so what we did was we did this plot for all of the galaxies in our sample. We divided the galaxy into these different components, and then we took the fraction of mass that we have in each component in the total galaxy and also within one effective radius. One effective radius is the radius where we have half of the light coming from the galaxy. So for example, something like this. So we did the same thing for the orbits, we selected this region and calculated the fractions in this region. Why one effective radius? Because in observations, that's usually what we look at. And so to make sure that we were comparing apples with apples, we selected that region as well.
Julia, how did you measure? Did you measure the effective radio, or were they provided with an eagle?
So they were provided in eagle, but these are technically not effective radius in the sense they are not the radius where you have half of the light, but half of the mass. But we also have, for the mock observations I had before, that I have after, for those we have effective radius measured in a similar way as we do for observations. So they're actually effective radius measured with the light, but not in this case. All right, so once we have that, so we measure the fractions of each of these components, cold, warm, hot, and counter-rotating, for our galaxies in our sample. And then we plot them, of course, as a function of mass. The first thing, there's a lot going on here, but the colors are as before. So red is the hot orbits, orange warm, blue are the cold orbits, and green the counter-rotating. Then we have fraction of orbits within one effective radius on top, and the total ones, so for the whole of the whole galaxy at the bottom. They're more or less similar, within one area or in the whole galaxy. It changes a little the absolute values of the peaks, for example. But what was interesting for us, if we look at the whole sample of galaxies, is that we have the diffraction of both cold and warm orbits are increasing up to a certain point, and that's around stellar mass 10 to the 10.4, and then they start decreasing. On the other side, we have the diffraction of hot orbits start increasing at that point, and counter-rotation as well. This was interesting because that's also the stellar mass, around the stellar mass where we see from simulations mergers becoming important in galaxy evolution. So we divided our sample into galaxies that had minor or major mergers, any since redshift 2. That means that the galaxies merging together had to have a mass ratio of at least 0.1. Anything below that wasn't considered, and then all the other galaxies left. As you can see here, we still have this similar trend. The points are more or less of the same mass as well as before, because this is not really, so the lower masses are not really affected by mergers that much. But if we look at the no mergers one, we see that the peak is moved to 10 to the 10.7-ish. We do still see this change in trend as we've seen before, but looking at it in more details, we found that that was due to the very minor mergers. So if we exclude all type of mergers that a galaxy had, the curves would keep going in the same way without any change in point. So the cold orbits will keep increasing, only they will probably stop around here. We didn't have many in this region anyway. There were like 100 galaxies out of the 3,500 that we had. But yes, so that was interesting to see. And it looks like mergers do have an impact on the fraction of orbits. So keep that in mind for the future and for the next few slides. Then we look at the ages of these components. Sorry, I forgot to mention that these are the median values with the scatter. You can't probably see that much in here, but again, we have same colors as before. So this time we look at the ages of this component. The age of a component can tell you how long ago it was formed, or better, when it stopped forming. And so we have that in general. The hot and counter-rotating components are always the oldest ones. If we look at the non-mergers sample, we see that there's a little bit more difference between the two compared to the ones mergers, and that the cold component is always the youngest. Again, if we have mergers, the curve changes a little, especially if we look at the whole galaxy. So it looks like the outer disks of galaxies are being continue to grow, even though the inner regions have already finished growing. Was that?
Hi, Julia.
Yes.
I was just wondering, how do you distinguish between merger and non-merger galaxies? Like on what timescales?
So it was any galaxy that had a merger, major or minor, from redshift 2 in simulations. So So you can check whether there was anything. We have the merger ratios as well, so it's just matching things basically. But the no mergers ones is actually also galaxies that had mergers with mass ratio below 0.1. So very minor mergers as well. Yes. And so since mergers look important, we had a look at how these fractions of orbits and their ages change with number of mergers. So this time we have the median values here for each orbital component as a function of number of mergers. They're slightly offset just because it was easier to see them, so there's nothing going on in there. But as you can see, especially if we look first at the fraction of orbits versus number of mergers, they kind of look consistent to 0, but we do see some trend. In particular, the hot orbits look like they're increasing with number of mergers, while the and the counter-rotation as well, while the cold orbits are decreasing. So the solid lines are within one array, and the dotted points are the total for the fractions for the total galaxy. And similarly, the warm fraction are also decreasing with increasing number of mergers. So this seems like mergers could disrupt cold and warm orbits, making them more into hot and counter-rotating orbits, or maybe it means that these hot and counter-rotating orbits, so the stars that are created from the galaxy, will end up being into more chaotic orbits than what we have in the main galaxy. That's why we have an increase maybe in the fraction of orbits. So for the ages, we see that all of them kind of decrease, and that's mostly depending on whether we have gas or not in the galaxy, and whether the galaxy itself is younger. So if it's less massive, it could be younger than the progenitor, and so we have a slight decrease in the ages as well. But yes, so mostly is gas being funneled in the galaxy center, leading to new star formation and making the average values of the age a little younger. So now that we know that there's something going on with merger, but I said it depends whether there's gas or not, or other things. What we wanted to look at was whether there's any particular difference depending on the type of mergers that we have. Just a quick recap. I know that I already mentioned some of them.
Julia, sorry to interrupt the next bit. I was wondering, do you have these plot size for the next mass, like for higher mass?
I have them for the different mass spins as well. Yes.
Yeah.
So I have the highest one. They're very similar. This is the one where the trends are the strongest. Mm-hmm. But it's not that different for the highest mass as well. But I have them in the paper. I think we have them in the appendix. Yeah. Otherwise, I can send them to you if you want to see.
Thank you.
No worries. So yes, type of mergers. So we can have major mergers if we have a mass ratio. So if two galaxies similar size similar mass merge together, that means a mass ratio above 0.3 in our case. That's how we define them. Minor mergers if the mass ratio is between 0.3 and 0.1, the other way around, 0.1 and 0.3. And then wet mergers if we have gas involved at all in the merger, and then dry mergers if none of the galaxies have gas coming into them. So we had a look at the differences, same plot as I did before, but for minor mergers and major mergers, we didn't find anything there. But when we look at the differences of the fractions of orbits for number of wet mergers and dry mergers, we did find something. And so, for example, if we look at the fraction of orbits as a function of wet mergers, we see that there is a little bit of increase for the hot orbits, so the orbits are more chaotic with more wet mergers and a little bit more of counter-rotation as well. And similarly, we do see a decrease in the other two fractions, but it's not very strong and it's incremental, so it gets bigger with bigger number of mergers. Well, if we look at the dry mergers, this time we see that even with just one merger, the fractions changes a lot. In particular, if we look at the hot orbits or the counter-rotation, it gets to very high values, especially we found that the highest values of counter-rotation, are usually, we usually need a dry mergers to get to those. And similarly, the cold rotation, the cold component goes almost to 0. And yeah, as I said before, even with just one dry merger, we get a great impact on the structure of the galaxy. So the stars in it, their orbits will change, how they are distributed will change a lot. Just to sum up this first part of the project, we analyzed ego galaxies, about 3,500, and look at how their orbital components changed with mergers, the connection with them, with the orbital components and the mergers. And we found that the fraction of orbits have a connection with the number of mergers that the galaxy experience, in particular with the dry mergers. We see a very strong effect in the orbital fractions with dry mergers, so that the fraction of both orbits and counter-rotating orbits increase, and we see a decrease in the fraction of warm and cold orbits. So that the galaxies are less disky and more round or triaxial in shape. But then this was the first part. So the second part, what we wanted to do was to derive these orbital components in a similar way for both simulations and observations. And it's a lot more complicated than what you would expect. So as observations, we wanted to compare them with galaxies in the MAGPI MAGPI survey. This is a large MUSE program of galaxies, a redshift 0.3. Since it's integral field spectroscopy survey, we don't have just one value for each galaxy, but we have the 3D data cubes. So we have the spatial distribution as well. So you can see here an example, one of the maps with surface brightness, velocity dispersion, H3 and H4, for example. As you can see, it's a 2D map, so you can have the spatial information as well. And we use this as an input to software called Dynamite here. It's a dynamical modeling, spatial dynamical models, orbit-based, in order to reconstruct the property of the galaxy. We have a 3D model where we can get all the information about the intrinsic properties and the orbital distributions as well. And as I mentioned before, that was the thing that we were interested in mostly. But how do we compare it with simulations? Because for simulations, first of all, we wanted to make sure that we were comparing things using the same method. So we removed all of the biases coming from measuring things using different ways. So we use SynSpin. Since MAGPI actually has some theory data sets as well. So it uses for simulations and has mock observations of these 4 simulations coming using SynSpin. SynSpin, Kate Harborn from UWA developed it, and it's a tool that allows us to use, it's kind of like a virtual telescope that allows us to look at galaxies in simulation in the same way as we do for observation. So you can set your virtual telescope to have all the same parameters as, for example, MUSE, and so recreate maps in a similar way as what we find for MAGPI. So that's what we did. And so we took these mock observations of ego galaxies, selected them to be as similar as possible to MAGPI, and then used the DMR software, so dynamical modeling, to study all of the properties of these galaxies, and then compare them with the dynamical modeling applied to actual MAGPI galaxies. So, one thing at a time. First of all, since we were doing this, we also thought it was a good idea. It was a good way doing dynamical modeling on simulations, mock observations of simulation, to test whether what we got from the dynamical modeling was actually consistent to what we saw in the simulations. So that was goal number 1. And goal number 2, as I mentioned before, was to compare with the MAGPI galaxies. So we selected MAGPI primary targets. So our galaxy is able to match MAGPI primary targets. Then we had some quality criteria to make sure that what we were getting, since, as I mentioned before, we were looking at fraction of orbits at 1 effective radius. We wanted to constrain our data up to at least 1 effective radius, and then make sure that they were well sampled. So they had enough number of bins to get robust results. You can see here that we had on average about 100 bins for galaxies within 1 array. Most of them covered a larger area, so they had even more bins in total, but that's for just the total. Although most of our galaxies were in the mass range above 10 to the 10.8. They will come back when we look at MAGPI galaxies, but there was the best that we could do with the sample that we had. And so we end up having 75 MAGPI-like galaxies, and not the 150 that I mentioned in my abstract. But yeah, that's still good enough to have a look at what we were doing. It's still better than what MAGPI had, but only 22 galaxies, so I can't really complain. But yes, so to just give you a brief description of the dynamical models that we use. This is going to be very, very quick. If you have any question about this, I'm happy to talk about it because it's a lot more complicated than what it seems. But basically what these models do, they take observations of a galaxy and then they create orbits to populate the galaxy and integrate them and weight them in order to reproduce the maps that we see. That's like the simplest way, simplest description. So we did something like that using the mock observations created by Kate. So you can see here an example. One of the observations that we had, the data again is surface brightness, velocity dispersion, H3 and H4, and the best fit model that we got from Dynamite. Now, what we want to do, since we can have a lot of data from a lot of properties from these models, we just wanted to select some of them and have a look how well they compare to the actual data from simulations. So, for example, some of the properties that you can get are the intrinsic shape of galaxies, since we're building a 3D model, and then we have whether the galaxy is radially anisotropic or tangentially anisotropic, so whether it's rotationally supported or pressure supported. And then we can also get information on the internal mass distribution, so not just the stellar mass, but also the dark matter content of the galaxy with the radius. And lastly, since that's what I've been repeating for the past half an hour almost, the orbital components. So again, cold component, like a thin disk-like component, warm component, and like a thick disk, hot component, bulge-like, and counter-rotating component, similar to the warm and cold, but rotating on the other direction. So again, we measured, just to remind you, this is how we measured our orbits. So the more similar to the circular ones were called cold. Warm one are the ones in between cold and hot. Then we have the hot and counter-rotating. And the tricky bit was that the way the orbital distribution is created in simulation and in the dynamical model is not the same. So you can't really compare what you get directly from here to what you get from the modeling. So we had to go through a few steps there. Again, I'm not going to go into that right now, but if you're curious, I have plenty of extra plots for that as well. It was quite tricky, but we got there. At least we did the best that we could without having to spend 100 hours for each galaxy. So again, we measure all the orbits, this time only within one effective radius. And this time the radius is an actual effective radius. So based on the light coming from the galaxy. So first of all, we checked whether the masses that we got at 1 array, everything that we'll see is either within 1 array or at 1 array. So we checked whether the total mass that we got from the model was consistent with the one that we got from the simulation. That's the x-axis. As you can see, there's a bit of scatter. It's not too bad. So they generally recover quite well with a median offset of 9%. It was pretty nice to see. But if we look at the dark matter on the right, you can see there's huge scatter, first of all, but also lots of times it was underestimated. We got a median underestimation of 48%. And that's something that we've been looking into for a long time. The main reason why we have this is because with the dynamical modeling, you have to assume a certain distribution for the dark matter. And usually what we use is an NFW profile. However, even looking just at simulations and the NFW profiles done for these galaxies in Eagle, not with the dynamical modeling, just playing fits on the data, they don't look really great. If you go in the inner region of the galaxy, if you go at the outer region, it's perfect, it's fantastic. But the very inner region, it's just not working. And so this is one cause, but also sometimes it's been shown before in the literature that the dark matter distribution is not spherical as we assume it. Most of the times follows, especially in the inner regions, the shape of the stellar distribution. So if it's a triaxial shape, the galaxy has a triaxial shape, especially in the center, we'll have the dark matter following that as well. And we assume a spherical distribution instead, we can get very different results. So this huge scatter that you see is mostly due to that. So we check in particular those galaxies at the lower points, and those are all galaxies where the NFW profile just looks. So the NFW profile from the modeling looks really similar to the NFW fit to the particle data, but it doesn't look anything like the actual dark matter content of the galaxy.
So that sounds like the model's wrong there, rather than the
Yeah.
Schwarzschild fitting.
Yes, exactly. And so we actually have some ideas to better explore this, but it's going to be a huge project. So it's nothing that I was about to do here. But that's something that we're keeping in mind because we have many ideas of how to address it. Hopefully, at least understanding how to address it. But yes. And then we looked at the intrinsic shape at 1 array, just to give you a very brief idea. We divided the shapes into oblate. These are, for example, this galaxy or galaxies where in general you have that the z-axis is shorter than the other two, but the other two are the same or very similar. Prolate galaxies are these elongated objects where the z-axis is the longest axis, while triaxial are these shapes where you have all three axes of different size. And so we use the triaxiality parameter to categorize these shapes, and this is defined using the axis ratios. So P is the minor to major axis ratio, and Q is the minor to major axis ratio, and P is the median to major axis ratio. And so if we have a value of T that is below 0.3, we say that the galaxy is oblate. If it's between 0.3 and 0.8, it's triaxial. Above 0.8 is prolate. And so we had a look at how well we can retrieve these shapes from the dynamical models. Again, we have the values from the model on the y-axis and the true values on the x-axis. So the points that are colored are the points where the shape, the classification is the same for both the modeling and the true values. So the magenta ones are the oblate galaxies, purple triaxial, and the blue are prolate. The gray ones are where the classification from the model went wrong. So we have that 73% of our galaxies have been correctly classified from the model, using the values from the model. We have a median upsell of 0.07, that it's not huge. It's not the best because we also have lots of like a huge error bar sometimes. But most of the cases, like 85% of the cases where the classification went wrong was because we have galaxies with a very low viewing angle, and the modeling doesn't really handle that well, the dynamical modeling. It doesn't really understand if a galaxy is close to face-on, whether that's a real face-on galaxy or maybe at this galaxy with a big bulge, like an edge-on galaxy with a big bulge. And so it gets a little trickier. But we're still not too bad, I'd say, especially from what we knew before, what we were expecting at the beginning, what we got at the very beginning. It was actually quite good to see. And then lastly, we had a look at the fraction of orbits within one array. We have here, as I said before, comparing fractions of orbits directly from simulation and the modeling was very tricky. But in the end, this is what we got. So cold orbits and hot orbits and counter-rotating orbits are not too bad. So we have median offset of 0.2 for the counter-rotating orbits, 0.6 for the hot, 0.7 for the cold orbits, but the warm orbits are consistently underestimated. This mostly has to do to how we make the orbits from simulations. The orbits from a simulation are instantaneous, so exactly what you see right now, while the orbits from the modeling are time averaged over a certain period of time. And so they, especially if you have some orbits that are not exactly circular, it's not that easy to make the comparisons. We try to average them in particular ways, but there's still something there due to the fact that they're not exactly the same thing. So we're not exactly comparing the same thing here, but it's close enough. And from what we were doing was actually pretty surprising, and especially after the first results. So at least we can see that there's a lot of scatter, but in general, if we study a population, they go in the way that we expect. And so after this, we compare our results with what we got from MAGPI. So MAGPI had 22 galaxies that were analyzed by Caro Derken at the Macquarie University, and those are the gray squares here. And while our galaxies are the blue circles, as you can see, the distributions of the two are very different in both stellar mass and radius. So we're going to see differences for sure. Some of them are caused by this difference in sample size and distribution, but some of them are just different. But that's also what we wanted to see, whether there was anything that we could see in the simulations that maybe needed checking, or if we could learn anything from that. So first of all, the dark matter. We checked the fraction of dark matter. This is the dark matter within one array over the total mass within one array. Again, the both points, gray squares, are the median values for MAGPI galaxies for each mass bin, and then we have the blue points. There are the median values for Eagle galaxies. If you look at stellar mass above 10 to the 11, it doesn't look too bad. There's a lot of scatter if you look at the individual points, and the error bars are huge. But we know that before dark matter, it's very hard to constrain if you don't have especially the outer regions of the galaxy, or gas to give extra constraint on that. But we look at the stellar masses below 10 to the 11, it looks terrible. This is mostly because we don't have many galaxies, for sure, but also because the median values don't really take into account the huge error bars that we have there. Taking these into account will probably bring our points a little bit lower. Yes?
So those fraction dark matter zero galaxies from MAGPI, I suppose, is that reliable? I suppose to believe that? Or?
That's a very good question. You should ask Caro, because I have no idea. I wasn't entirely sure as well. It's just that the best fit gave that. I mean, it's a lower. Sometimes you have the best fit, that's the value, but you have the other fits that are quite close to the actual best fit. So it can be anything in there. It just means that it's very, very low. It doesn't have to be zero, but just very low within the inner region of the galaxy.
Because it does feel like those are what's dragging your median down as opposed to the ones that seem to be scattered.
But again, you only have 22 points there.
Yeah,
and in this area, you have 4. So we need more galaxies, more people to do this for the other galaxies MAGPI. But if we look just at the median values for both Eagle and MAGPI, the whole sample, they're actually consistent. They're different, but considering the errors, they're consistent. Still, there's a lot that has to go into this for sure. Again, because the dark matter fractions also might not be correct, even though they have the same problems for the observations and the simulations. But as we've seen in the simulations, these fractions are probably wrong for some of these galaxies. So I don't know how to trust this. I wouldn't trust it at all. But yeah, anyway, can give you an idea more or less of how much dark matter you have, but that's about it. But for the fraction of orbits, fraction of orbits and shapes work actually pretty well. So since Caro found this connection between the triaxiality and the fraction of orbits, so that the higher fraction of orbits a galaxy had, the more triaxial it was. This means that it's the galaxy that has more chaotic orbits, more pressure supported, is less disky. And so we did a similar thing, but with all of the fraction of orbits that we found. We have the squares, MAGPI points and circles, Eagle points, and triaxiality here, as I said before, between 0 and 8 are prolate galaxies. Triaxial between 0, 3 and 0.8, and between 0 and 0.3 oblate. So they found a very strong connection between triaxiality and hot orbits here. We don't see a connection that is as strong as theirs, but there's still a connection there. Our strongest relation, though, is with the fraction of warm orbits, so that with the decrease of the warm orbits, we have an increase in triaxiality. So definitely galaxy, and also the cold orbits have a very strong connection, so that galaxies are less disky if we go to higher fractions of hot orbits and lower fraction of warm and cold orbits, as we would expect since we have less stars on disky orbits, but no connection at all with the fraction of counter-rotating orbits. But still, it was nice to see that we found similar things, at least for that. So galaxies in both Eagle and MAGPI have this similar connection between triaxiality and fraction of orbits, so that we have most of our galaxies in general are very triaxial, and for MAGPI as well. They have 80% of the galaxies that have triaxiality above 0.3, We have 67%, if I remember correctly, something like that. So the majority of them are triaxial or non-oblate at least, and they're supported by hot orbits. Then lastly, we had a look again, similar to what we've done with the simulations, since we're using mock observations, but they're still simulations, so we can go back in time. We check the fraction of orbits against the number of mergers that they had, this time between redshift 0.3 and 2, because our mock observations were a redshift 0.3. So we can see again, this can be consistent with zero short, but we can see like suggestions, trends with the number of mergers. Of course, we have fewer galaxies that had 3 or more mergers. In general, we have 69% of the galaxies that had at least 1 merger, and 31% that had 2 or more mergers in their life. Not in the life, sorry, up to redshift 2. So if we look at these galaxies in particular with 2 or more mergers, we see that the change in the fraction is actually quite a lot. So for example, from here to there, we have a 30% more mass in hot orbits. If you look just between 2 and 3, it's actually more than that. And similarly, we have 70% fewer mass, less mass in the hot component, warm component if we go from 1 or less mergers to 2 or 3 mergers. So again, what we wanted to do was check whether there was any difference between wet and dry mergers. And we found that galaxies in our sample mostly had wet mergers. Only 35 of them had 1 dry mergers, no more than 1. Very, very few had 1 major dry merger. As you can see, as we saw before, there's not really a connection with the fraction of wet mergers. You need more than just 1 to see something. While even with 1 dry merger, you do see something. So the galaxies here are galaxies that only had wet mergers and only dry mergers on this other side. So you don't see whether there's anything that it's the combined effect of both. But it was interesting to see that it's not super great, but you do definitely see a decrease in the fraction of warm orbits with the number of dry mergers. That was most of what we've done. There are other results in the paper that I've submitted as well, but this was the short version. We found that what we can get from the dynamical modeling is mostly reliable. Dark matter, not really, but it's not really a problem of the dynamical modeling. It's more like the actual assumption used for the dark matter that creates problem. And we found that Eagle and MAGPI will have galaxies that are mostly non-oblate and are supported by hot orbits with not many cold orbits. But we do find some differences, for example, in the fraction of dark matters at lower masses. And that is everything for me. Sorry for taking up so much time. But if you have any questions, I'd be happy to answer. Yes.
We don't have questions. I'm actually just going to say I'm amazed at the consistency between the models and the simulations. Like it's really great to see, and it's really great to see that test is done, because then you can kind of be like, yes, because it's such a. I mean, I saw how hard you worked during your PhD, but you know, it's such a black box, and it goes in and it does these fits and it shoves stuff out, and you're kind of like, well, it kind of makes sense, but it's really great to see these tests.
I was actually very, very surprised the first time that we got something that was consistent.
Yeah. And then the similarity then to kind of see with MAGPI is really.
I also have a plot with the similarities between SAMI and Eagle that I've done a while ago, and even for redshift 0. So these are Eagle galaxy redshift 0 are the ranges and the squares, and the triangles are the values that I got again for the orbital fractions for SAMI galaxies, and they look quite good.
And just for the audience, the SAMI galaxies are these are lower quality observations. More galaxies, lower quality, whereas MAGPI.
I mean, it's not that different in quality.
For some reason, I thought MAGPI was higher.
A little bit, but not that different.
Not that different. Okay.
Just a higher redshift, so it's really good for that redshift. But in my opinion, at least the mock observation that we had were similar to SAMI.
Okay. Yes.
So I was curious about the different effectiveness of the dry merger versus wet merger thing that you mentioned.
Yeah.
Is that saying that when gas is accreted, it's sort of a lot of the energy goes into that.
Yes, also it depends on the inclination of the merger as well, the inclination angle of the merger. But if there's gas, usually it tends to go into form these key kind of orbits. In certain cases, you have these key orbits but counter-rotating. And so we actually had a look into that because I had a few galaxies, not even mergers, even if you have just inflow of gas at particular angles, you get the extra counter-rotating orbits that you don't expect to have without mergers. It was very interesting to see. It's just a very small percentage of the galaxies that we were looking at, maybe 8%. But yeah, it was puzzling at the beginning, but then we realized it's if you have a very low inclination angle of the inflow of the cold gas, then you get this counter-rotation. Yeah, but yeah, so it's mostly because of the gas-forming stars in cold orbits. While if you have mergers without gas, so because you keep creating stars in the other orbits as well, but since you're forming also stars in cold orbits, you don't see that much difference in the total function. Yes.
So what is the impact of orientation of the merger on gravitational behavior?
So for the counter-rotating orbits, it's the low inclination. For the other mergers, we haven't looked into that in detail, so we don't know yet.
Yeah.
But it might be something that I can look into in the future. So sorry, I don't have an answer for that yet.
Julia, I have a question. So were you or are you planning to compare total mass profile between simulation and observation? For example, do you have any comments on bulge halo conspiracy that says that early type galaxies maintain a total profile slope of 2, total power law slope of 2, minus 2?
I know that Ken has been looking into that, but we haven't done that in simulations, with the simulations. And the thing is, I'm ending my contract soon, so I probably won't have time to look into that. But if I do have time, if I find something, maybe I'll look into that as well. But no, the answer is no, we haven't really. We weren't planning on looking into that yet. But Caro has some comments on that from the observational side, though. Yeah.
Okay.
The paper just got accepted actually a couple of days ago.
Okay, yeah, I'll check that out. Thank you.
I noticed, for example, on the slide just after this one, that the amount of cold and warm and hot and counter-rotating stars are very correlated with each other. What's up with that? Like, what is like a certain point where you get to a certain hotness where it suddenly switches from this category to that category in terms of just fraction of occurrence?
So we looked into that a little. I have another plot actually. So what changes mostly? It's not some orbits are being moved from they can be heated, but so they go from cold to warm or hot or whatever. But in most cases, it's because so you have here the fraction of orbits, but they're color coded by the fraction of XC2 stars, so stars that you get from other galaxies. So you can see that basically, especially after the mass that we were talking about before, 10 to the 10.5, where you have lots of mergers, your fractions are increasing, the fraction of orbits, because you have lots of stars coming from external galaxies, and those go into hot orbits. So it's connected in the way that you're increasing the hot orbits, so that's why you see a decrease in the cold orbits. They're not actually decreasing, it's just that the fraction relative to the total is less, but the actual mass is similar.
Okay.
So yeah, that's it. You might have some being heated up as well.
How much does it depend on the mass of the merger? Because we've always kind of been told that kind of more major mergers have more impact. But
When I looked into major and minor mergers and the differences, we didn't really see any difference. But yeah.
Yeah, I had a question somewhat related to that. So I noticed in a lot of the fraction of each kind of orbit mass plots, when you were looking at merger versus non-merger, qualitatively, didn't they look like quite similar in terms of their shapes and stuff? And it was just like the extent to which the hot and counter-rotating orbits were shifted up.
Yeah,
That was-
shifted in mass as well.
Oh,
they were
right.
a little shifted in mass as well, especially if you look at this plot here, you have the maximum that is around 10 to the 10.7, while here is 10 to the 10. Actually, that one is still there. 10 to the 10.4. Yeah, more or less the same. They slightly shifted, especially if you look at the hot orbits.
Right.
But also, this goes up because of the very minor mergers. If you don't consider those, then they keep going down. You won't see anything up above after this, because we don't have galaxies. They had nothing at all
Right.
above that mass.
So I guess like you would be confident that mergers plus very minor mergers are the things that are driving this sort of
Yep.
intrinsic change in,
Yep.
in the various fractions. There's
And
like,
that makes sense because you
Yeah.
can't really get to those. Well, I mean, some maybe, but most of the very massive galaxies come from mergers.
Yeah.
They will have experienced some accretion of mergers. And
but like whether those mergers happened before Redshift 2 or what.
we haven't checked on anything about before Redshift.
You don't, you expect the ones since Redshift 2 to have had the most impact.
Right, yeah.
This is, sorry.
Sorry, hi. Just wondering whether you've also looked at the like intrinsic disk structure of your disks. Like, do you have bars? Do you have how many arms?
In
do you have?
Eagle, it's tricky.
It's hard because the resolution, right?
Yes, and so it's a little tricky to do that in Eagle. We have a student that is gonna do a similar analysis with other simulations as well, so they might look into that. For us in particular, we tried looking at galaxies visually in Eagle and classify them as spirals or things like that. It's just there are not many that you can actually see and be sure that there are spiral galaxies or have a bar at all. And some of them look like it's just a bar and nothing else. Like we have these elongated shapes with nothing around it. It's very weird, but yeah, anyway.
Oh, I was just gonna say, it's really nice to see like a visual representation of how the orbits, we've had this picture of how the mergers change galaxies, and it's nice to kind of have this really visual picture of the impact on the orbits and what that is from mergers. So that's kind of,
Especially also for the shapes, it was predicted to have a great impact on the mergers, to have a great impact on how we form probably galaxies or triaxial galaxies. And since they're connected with the shapes, we see that there is actually a connection with them as well.
yeah, it's nice to have that evidence.
Yeah.
Any last quick questions? All right, well, let's thank our speaker again. If you do have some more questions, will you be hanging around for a little bit?
I'm there next to Aman.
Yeah, upstairs, next behind Aman. And the thing that Ryan wanted me to say was that the rest of the speakers until November are also ASA, ICRAR Symposium people. That's the first of many. So, thank you.
Thank you. Thank you for having me.